Let's talk a little bit more about some example problems. So if we have changes in mechanical energy for non-conservative forces, meaning mostly friction, the other way to write this is you can still have potential energy. So we're just adding terms back and showing different parts of this equation. Remember, the whole equation is always this on one side and all the possible energy transfer mechanisms on the other side. But because this class is a mechanics class, these are the ones that come up the most, okay? So this is a little bit simpler. So let's try another example problem. We have this 5 kilogram box attached to an end. Now we have a spring, and we know the box is at rest at the equilibrium position, and we pull on it with a rope. So this is going to require a lot of drawing, okay? The biggest difficulty of these problems is keeping track of all the crap in the problem. So we have a 5 kilogram box. It's attached to one end of a spring with a spring constant 80 newtons per meter. So how are we going to draw this? Well, we have to draw the before and after, and then we have to keep track of all the things happening before and after. So let's start with that's not even the right thing. Terrible. Drawing's hard, guys. Okay. So here's our 5 kilogram box. Okay, here's our spring. And then we have a rope with constant tension this way. Okay. Why does the rope have constant tension? Just mostly to make the math easier, right? Okay, so this is our before situation. In our after situation, let's see. Let me make this pretty. The box has pulled away from the wall. So here's our box, here's our rope, and here's our spring now pulled a little bit differently. We'll just draw some lines here so you can see the displacement. So first things first, we have our displacement. That's delta x, which is equal to what? Yeah, this should be 50 centimeters. So 0.5 meters, just to save conversion later. We know we have a tension both times. That's going to be T. And we know that T is equal to 100 newtons. Let's see, spring constant. Our spring constant we'll just write in purple, I guess. So K is equal to 80 newtons per meter. And then we know that the coefficient of friction, mu K, is going to be 0.3. Okay, so what do we know about velocity? Because remember, we also have to deal with kinetic energy. So let me write these out as initial and final. This is initial, and this is final. Okay, what's going on with the velocity in your initial situation?
Does it start at 0?
Yeah. So v initial is equal to 0, and later we have some v that we don't know. That's what we're looking for, okay? We want to know what is the speed of the box. And anything else? I think that's it. So we just have to start with our equation. So our equation, and let me move this over. Our equation is going to look like work on one side is equal to change in kinetic energy plus change in potential energy plus change in internal energy, which of course is friction, okay? That means we're choosing what as our system? So what's included in the system?
The spring.
We'll include the spring, okay? We'll include the ground because we want to make sure we account for all the internal energy and the block, obviously, okay? If we don't include the spring, it changes things a little bit. It's much easier to include the spring because if you include the spring on this side as work, what do we know about spring force?
It's constant.
It's not constant, right? So that means if we calculate the work on this side, we have to do an integral. If we calculate the spring as potential energy, we don't. So there's a good reason to include the spring mathematically because it makes your life a little bit easier, although you do know if you integrate kx, you get 1/2 kx squared, so it wouldn't be a difficult integral, okay? So that means we have to calculate the work. What is the thing doing the work?
The tension.
The tension, okay? So we want to calculate the work. That means we have tension times what? How do we get work? Force times what? Distance. So tension times delta x, okay? What about our kinetic energy? We have a change in kinetic energy. We have a final kinetic energy, but our initial kinetic energy should be 0. So that's just 1/2 mv squared, okay? What about our potential energy? What's our final potential energy? So no, it's still moving, right? So this, what's going on with the spring?
It's getting stretched.
The final position is stretched. So that means you want 1/2 k delta x squared minus the initial position, but that's the equilibrium position. So that's going to be minus 0. So we just leave this term like this, okay? And then last but not least, we have our friction. In this case, because we know, and we can draw this out, this is just normal force and mg. We know normal force should be equal to mg. So friction should be mu mg delta x, okay? That's the frictional force times the displacement, okay? Conveniently, all of our delta x's are the same. That doesn't have to be the case, but in this case, the spring is stretched that distance, the tension is pulled over that distance, and the friction happens over that distance, okay? Cool. So if we want to solve for this, we do some algebra and we solve for velocity, okay? Because velocity is the thing we're solving, we're asked for in the question. So that ends up being, there's lots of x's. So if we do a fair amount of algebra, I'm going to skip through that. That's going to give us 2 over the mass of tension delta x minus 1/2 k x squared, that's a delta x squared, minus mu mg delta x. And then we just plug in a lot of numbers. So 2 over 5 kilograms, 100 newtons times 0.5 meters, geez, I'm gonna run out of space again, minus 1/2 times 80 newtons per meter, 80, not a very good 80. 0.5 meters squared. Cool, I've already run out of space. Let's move this over. It's a great thing about using an iPad. I'm still not gonna have enough space, but you get the idea. Minus, oh god. I'm gonna make this much smaller. This one's annoying, but not hard. So 0.3 times 5 times 9.8 times 0.5. I lost units, but I saved space, so there. Plug all that stuff in, plug it into a calculator, you get 3.6 meters per second. You can pretend I did that in my head. I do this ahead of time so you don't have to watch me clumsily enter them into a calculator. Okay. There's other ways to do this. You can sort of, because of this is so much plugging in, you can do these terms individually and then add them up at the end so that you have a general idea of like how much energy each thing takes. It also tells you a little bit about how much energy each thing takes. The other way you can set this up is if you exclude the spring, right, then the spring energy just goes into the work because it's an external force. Okay. Any questions on that? The key thing to getting these correct is just this part where you write down all the information in a way that you understand and you know everything that's happening in the initial part of the problem and everything that's happening in the final part of the problem. Okay? Is this difficult? Not difficult. Annoying?
It's a lot.
It's a lot, yeah. It's mostly annoying.
Okay, so we have a plastic cube. It's pressed against a spring, so you start out with spring potential energy, or if you, depending on where you put your boundary for your system, it could also be work done by the spring, but let's include it as a potential energy. We're compressing the spring by 10 centimeters. We know the spring constant. The cube is 22 centimeters from the bottom of a slope. Once the cube is released, we want to know what height the cube gets to. And we know the coefficient of kinetic friction on the flat surface is 0.2, and there's no friction on the ramp. So let's draw this out with the before and after. I'm just gonna draw this. Oh. Cool. Oh, weird. I lost the ramp. Okay. This has gotten really out of hand. Oh my gosh, why is it doing this? There we go. Okay, so that's our initial and final things. So let me give it some space. So this is initial. And then we're gonna make this final. Which means that the spring is there. This thing should be up there. Make this a little smaller. Okay, so this is final. So the spring goes from here to here. We call that delta X, and that is 10 centimeters. We also need to know from here to here, this is going to be delta Y, or we could just call, we'll call that delta Y. We know this distance from here to here is where the friction is. And that's going to be, we'll call that delta S. Okay. And that's 22 centimeters. We also know that at both of these spots, velocity is equal to 0, so there's not actually any kinetic energy happening. So we're going to pick our system, block plus surface plus spring, so that we can say there's no external forces here because so friction and spring should be included. So when we sum up all of our works, change in kinetic energy plus change in potential energy plus change in internal energy, we know first off this is going to go to 0. This is going to be 0. Our change in kinetic energy is actually 0 because since at the beginning and at the end we have a velocity of 0, it doesn't actually matter. You know, at some point in the middle this thing has a speed, but we're not talking about that point, so that's going to be 0. Our final kinetic energy is gravitational, and our initial kinetic energy is spring. That's our change in kinetic energy. And then our internal energy is mu k mg delta S. So this is our frictional force, and then this is this distance here because that's how far it slides. So that gives us our answer. You could also, you know, pick not the spring in here, and that would put the spring energy over on the work side, but we're not going to do that because that's annoying. So this becomes, and what are we looking for? And we don't have to worry about this part of the ramp because it doesn't have friction, so it's not included in this thing. So only this distance along the flat surface is included. And we want to know the height that it goes to. So we're looking for height. To what height? And that means delta y. Okay. So we're going to solve for delta y. So let's do some algebra. That's going to be 1/2 k delta x squared minus mu k mg delta s. So y is equal to 1/2 k delta x squared minus mu k mg delta s over mg. That gives us 1/2. K is 25 newtons per meter. Delta x is 0.1 meter squared minus 0.2 times mass, which is 0.05 kilograms, 9.8 meters per second squared, 0.22 meters, that's the friction distance, and then 0.05 kilograms and 9.8 meters per second squared. Left out some units just for space. You add all this together, you get 0.21, meaning it went up 0.21 meters. And that is our vertical distance. Now the thing to remember is if this part of the ramp had friction as well, we'd need to find that distance as a function of y, which would require a little bit more trig, and we'd have to add it on to this distance. But because it doesn't have friction, this distance only depends on this right here, just the part where there's friction. Okay.